What we're going to do today is we're going to sketch this rational function using our first derivative and our second derivative to help us to graph it without a calculator. All right, so first thing that's useful when we're sketching a rational function is to find the x-intercepts. To find the x-intercepts, we set the function equal to 0 because we're plugging 0 in for y. Okay. Now this looks a little scary to solve, but if you just multiply both sides by x squared minus 4, because that denominator there is what's making it a little hard to solve. This crosses off, and then 0 times x squared minus 4 is just 0. Okay, and now we have something that's easy to solve. So I can take out a 2. I have x squared minus 9. I can continue to factor this. X plus 3, x minus 3. 2 cannot equal 0. X equals negative 3. X equals positive 3. Okay, so my x-intercepts are x equals 3 and x equals negative 3. Okay, now the next thing I can find is any asymptotes that this graph may have. So to find the vertical asymptotes, I set my denominator equal to 0. So my denominator is x squared minus 4, which is really x plus 2, x minus 2. So my vertical asymptotes are x equals negative 2 and x equals positive 2. Okay, the next thing I can find out are if I have any horizontal asymptotes. So if you remember back to when we graphed rational functions in the beginning of the year, the horizontal asymptotes had to do with the degree. So because the degree is the same top and bottom here, to find the horizontal asymptote, I divide the leading coefficients. So my horizontal asymptote is y equals 2 divided by 1 is 2. Okay, so that's everything that we can tell from the original function. In fact, we can go even further. If we want to get a y-intercept, we could do that too. So to get the y-intercept, we make x equal to 0. So we have negative 18 over negative 4, which simplifies to 9 over 2. So this is all information that's going to be useful when I graph. All right, now let's keep going. Now I'm going to find the first derivative. So to find the first derivative, I'm going to use my quotient rule. So let's actually write the function over again. Okay, the derivative of the top is 4x, and the derivative of the bottom is 2x. So I have to multiply x squared minus 4 times 4x minus 2x squared minus 18 times 2x. So I have 4x to the third minus 16x. This is 4x to the third minus 36x. So this is negative 4x to the third plus 36x. So the 4x to the thirds cross off. I have negative 16x and 36x, so I have 20x over, and then it was g squared, so x squared minus 4 squared. This is my first derivative. Okay, the first derivative allows me to find my critical values. So I'm going to set my first derivative equal to 0. Okay, similarly, if I multiply by x squared minus 4 on both sides, it's going to cancel this off, or I can put this over 1 and cross multiply. I get 0 equals 20x, so x equals 0. Okay, so now I can use these numbers on my interval to see what's going on with my graph. So I'm going to put 0 on my interval. And if you remember when we talked about rational functions before, we also have to put our asymptotes on the graph too. So that's 2 and -2. So I'm going to be testing 4 sections of this interval. Okay, so I'm testing -infinity to -2, -2 to 0, 0 to 2, and 2 to infinity. Okay, so if we test -3 into the first derivative, I get a negative number on top, and I get a positive number on the bottom. So negative divided by positive is negative, which means that we're decreasing on the interval. All right, now I'll plug in -1 into the first derivative. Okay, same thing happens. I have a negative on top, and I have a positive in the bottom, which means that I have a negative, which means the function is decreasing. Okay, let's check 1. Positive on top, positive on the bottom. Means the whole function is positive there, which means the function is increasing at that point. Okay, and then similar, positive, positive, which means I have a positive. So I'm increasing on this interval. So I'm getting a whole lot of information now as I go along.